Great, thank you very much. Well, if we had known you wanted a panel, John and I could have argued back and forth a lot. But anyway, it's really great to be here. This has just been an outstanding conference, and we've learned a great deal. I think one of the things that strikes us in comparing cybersecurity with physical security is how, even though physical security, the realm we work in, is many thousands of years older than cybersecurity, it's not nearly as developed or well understood. I think you young whippersnappers with your computer technology have done a really good job given the challenge you face with cybersecurity. Part of the problem in physical security is I think the best minds go over into cyber, leaving only drooling morons like ourselves to work on physical security. This talk's basically a primer about tamper detection and about tamper-indicating seals. Then we're going to talk about attacks and vulnerabilities of seals. Now, just a caveat, we're not allowed to show specific attacks on specific seals, but we really don't have to. Our claim is that anyone reasonably resourceful is going to be able to figure out how to defeat seals, even seals used for very important critical applications. That's the case at least for current seals, the way they're currently designed and the way they're currently used. We'll then talk about what we think are better approaches to doing tamper detection, and we'll demonstrate a few things that are really just in the early prototype stages. Well, John and I are with the Vulnerability Assessment Team at Argonne National Laboratory, just outside Chicago. We work on a variety of different types of physical security problems for a wide variety of different sponsors. We try to look at not just the technology, but also the human factors and the human and the social organizational issues associated with security. In the end, as you well know, security is more about really the human factor than it is about the technology. Just quickly, some of the things we do. We'll talk about the seals and tamper intrusion detection we do. We do a lot of things with cargo security. We were the first to show that it's real easy to spoof global positioning system, not just jam. I think we were the first to suggest countermeasures, but of course nobody's using them. We've defeated a lot of different biometrics and access control devices, RFIDs. And recently we attacked an electronic voting machine from the voter's end. And why that's interesting is because it means you don't have to, as an adversary, understand the microprocessor, the firmware, or have any kind of access to the microprocessor or the EEPROMs. Remarkably, most electronic voting machines have little or no security on the voter's end, and the voter can reach in and fool around with electronics very easily. Other kinds of things we do: product authenticity, nuclear safeguards, a lot of vulnerability assessments, consulting, and again, the human factors issues. We work with industrial organizational psychologists to take a look at security culture and climate. Some definitions. A lock, of course, is a device meant to delay, complicate, or discourage unauthorized entry. Doesn't stop it, as you saw in the tool demos. Almost anyone can defeat locks if they're sufficiently motivated. On the other hand, a tamper-indicating seal or tamper-indicating device, TID, is something meant to try to leave behind evidence that there's been unauthorized access. Now, if you're like most IT people, your exposure to seals are probably more or less related to little sticky labels that you put on hard disks, computers, maybe on envelopes with passwords for end users. That, for the most part, is security theater. There's no effective tamper detection there. If the little sticky label doesn't even have a unique identifier, like an identification number or a serial number, now you're moving from the realm of security theater to basically magic and superstition. There are ways to make sticky labels have some kind of effective tamper detection, but believe me, you don't want to do it because it's a real pain in the butt. We'll talk a little bit about some of those ways. So when we talk about defeating a seal, what do we mean? We mean we open the seal and then we reseal without either using the original seal or using a counterfeit seal. But here's the key thing: it has to be done without being detected based on the inspection protocol that is being used. So attacking a seal is just attempting to defeat it. Now, sealing goes way, way back. Probably the earliest cavemen and women would basically smooth the sand in front of their cave, and thus they could tell when they left if a cave bear or some other people had gone into their cave and stolen their stuff. That's a type of tamper-indicating device. We know that sealing, though, goes back at least 7,000 years because you can find ancient seals in museums all over the world. Typically, the early seals were just some kind of pattern, sometimes geometric, or a symbol of an animal, imprinted on a piece of stone, wood, or bone. This would then get imprinted into clay and later on wax or resin to leave a unique pattern, which could be used to seal things. And then about 3200 BC, a real killer app came out. Some clever person decided to put the carving on a cylinder. Now you could roll the cylinder up and down and create a replicating pattern. Didn't really improve the security, but it was extremely cool. And that killer app lasted about 1,500 years, and to be replaced in about 400 AD by the lead wire or lead string seal, which you see in the lower right-hand corner. This was basically, you would take a string or wire, wrap it around the thing of interest, put the string or wire through a blob of lead, and then squeeze a pattern into the lead. And the idea is if someone tried to break in, they'd either have to cut the string or wire, which would be hard to repair, or they could tear up the lead, but then they'd have trouble replicating the imprinted pattern. And some of the seals, even fairly far back, are just magnificent pieces of work, like this Minoan gold signet ring from 1500 BC. The way this would work, in the early days when writing was invented, about 3500 BC, they wrote things on clay tablets and stuck them in clay envelopes, and then they'd imprint a seal pattern on the envelope, and that way you could tell if somebody had been opening your mail. If you had a container, you could wrap an animal's skin around it, tie some string, put the clay onto the string, and then again imprint your pattern. And if anyone tried to break in, they'd either attack the string, the animal skin, or the clay, and then they'd have to replicate that pattern. So documents could be sealed up. And the ancient Egyptians had this clever design with a woven box where there was essentially a wooden dowel that came in from the front. It had a hook that engaged a loop underneath the lid. They would rotate the wooden dowel. That would close or lock the lid. Then they'd put clay on the front face of the dowel, imprint the seal pattern. Now, if someone tried to break in, they'd either cut the woven basket, which would be detectable, or have to take the clay off in order to rotate the wooden dowel. But again, they wouldn't be able to replicate, at least in theory, the seal pattern.
Okay, so some more definitions. In the world of seals, a trap is a covert seal. So imagine, if you will, the hair in the door jam trick. That's not a really good technique if everybody knows it's there. They'll go grab the hair, go in the room, come out, put the hair back. So you want to be covert, stealthy. There's also the barrier seal. This is a lock and a seal all in one device. From our experience, you neither get a good lock nor a good seal from such a device. They're very easy to defeat. A tag is a unique identifier that uniquely identifies an object or container. For example, a barcode uniquely identifies a product at a store that you can go and purchase. Lifting is removing a tag and placing it on another container without being detected. Not being detected, stealth is basically the key for being the bad guy in the seals world. A seal is not a lock. It's not meant to keep anybody out. What it's designed to do is record unambiguously that tampering has been detected. It's usually done by some sort of damage that's on or around the seal. So yanking a seal off of a container is not defeating the seal, because if an inspector comes by, they're going to see the seal's not there. They're going to know something's up. Now, in our opinion, all seals should have a unique identifier. They don't, but they should. Also, since seals are supposed to unambiguously record that tampering's taken place, you should inspect it from time to time. A seal that's never inspected is pretty much worthless, but this happens in the real world. Now, defeating seals is mostly about defeating people. It's not like locks, safes, and vaults where you're actually going after hardware. Yes, you're going after hardware, but you're trying to fool a person. That's the end result of this. Now, a seal is only as good as the recipe in which it's used. All of these are very important in the seal process. You have to have a good chain of custody. On this list, I would call out how you install the seal and how you inspect it are very, very important. Unlike seals, a real-time monitoring system or intrusion system will, if tampering is detected, will automatically raise an alarm. What we see a lot in cargo shipments is they'll have real-time monitoring systems, but if your cargo's in Peru and it gets hijacked, if you've got no force to respond to the alarm condition, There's no real point in having a real-time monitoring system. You can instead spend your money on, other avenues of security. Like I said, if you can't respond, there's no point in having it. There are a lot of different kinds of seals out there. Nobody really knows how many. We think there are somewhere in the neighborhood of 5,000 or so. The applications vary. They're all over the board. You're probably most familiar with the seals used on products in the stores for like your drugs, your food, stuff like that. Those are all the seals, types of seals. Roger's going to pass out some seal examples. But before he does that, he has a couple things he wants to say.
Yeah, I'm going to pass out some variety of samples. Just a disclaimer. We're not saying these are good or bad. We're not saying vandalize them. We're not saying we haven't. They just give you examples of seals. Some of them are opened and some of them are closed. We'd ask you not to close the ones that are opened because, number one, we just have to open them and we have better things to do. And number two, the other people won't be able to see the mechanisms. So I'll just start passing these around.
And while he's doing that, I have an example up here of an electronic seal. This is sort of an expensive little guy. All it does is, right down here, you put a cable in these holes and turn it on, and it generates a number. The number in this case, 5318. So if at a later time somebody comes and takes the cable out of here, you get a new number. So you come back as an inspector and you have a new number there, you know somebody's gotten to the cable and gotten into whatever you're attempting to protect.
Yeah, where's the interface to that?
Say again?
Where's the JTAG on that?
It's visual. The inspector has to come and just look at it manually, just like we are.
No, I see it, but where's the JTAG on that? And I'll give you whatever number you want.
Well, you're absolutely right. In fact, there are easier ways than the JTAG, which I'll get into in just a second. But not specifically for this device because we won't call out or pick on specific products.
I'm also going to pass out a book that's got a bunch of adhesive label seals, and you can take a look. Some of these are very frangible. Others leave behind the word void, tampering, or locked if the seal's open. One of them, even before you open it, has this big scary do not tamper, which is no doubt its best security feature because it no doubt scares the adversaries away.
All right. We've looked at, the results I'm going to show you are the results of looking at, in depth, 244 seals in detail. Now, we've actually looked at hundreds of more seals than this, but the results are qualitatively the same. Now, we've looked at government and commercial seals. We looked at mechanical, electronic seals, low-tech from the adhesive label stuff you're seeing to very high-tech, where fiber optic systems are used and they're looking at laser light pulses, etc. There's a cost variance of several orders of magnitude. Some of these seals are several pennies. Some of these seals are thousands of dollars a piece. Half the seals we've looked at are used in some sort of critical application or some application that folks would consider to be critical application. And 19% of the seals that we looked at involve nuclear safeguards of some sort. The results of our research is that one person using very low-tech methods can defeat half the seals in a minute or less. They can defeat 95% of the seals in under 10 minutes. Oh, sorry. My bad. Coming up. Here's our graph. 50%. Thank you. 50% of the seals in under a minute. Now, remember, some of these things are thousands of dollars. What does that tell you? Well, we work for a national laboratory, but we've never had to use the resources of a national laboratory. What we do is we go to Home Depot. We go to the local dental supply store. We go to the artisan stores, paint matching, stuff like that. We've never had to get high tech on any of these seals, even the ones for nuclear safeguards, unfortunately. Here's some more statistics. The median attack time is 43 seconds. The average is a little under a minute and a half. The most telling statistic here is that we don't sit around scratching our heads trying to figure out how to defeat this stuff. The median time to develop an attack is 12 minutes. Here's some more charts for you. The top left chart there shows the attack time versus seal cost. It's a log-log chart. It's pretty scattered. There's no real good correlation here. However, if you believe that there is a slope of the line, what you get out of it is for every extra dollar you spend, you actually increase the attack time by about 270 milliseconds. So that's something to keep in mind if any of you want to go buy some expensive seals. Another chart, the lower right there, it's, again, there's not a high correlation there, but that shows the level of techness when it comes to attack time or defeat time. Now, the level of techness is pretty subjective, admittedly, but you see that there's no correlation. If you believe that there is a correlation and you want to use the slope of the line here, if you increase by one technology level, you increase attack time by about 170 milliseconds. One thing to note about the more complicated, high-end, high-tech seals is that it's more complicated, which means there are more avenues to go after as potential bad guy or hacker. So those usually fail epically compared to the adhesive label, which fail just by coming up without damaging themselves. Again, like Roger said, we're going to apologize. We're not going to show specific attacks on specific products. It's just sort of the name of the game. However, we can talk about general attacks. One of the number one ways to attack a seal is you pick it open. You can do this just with your fingers. You can do this with tools. There are solvents out there. A lot of different ways to do it. You might use shims. We've been known to use fishing line. Anything that works is fair game. Counterfeiting often works. If you actually destroy the seal that you're trying to get into, you just go find other seal parts that they've thrown away and use those to... So this goes back to chain of custody. When you get done using a seal, you don't just toss it in the dumpster. Somebody dumpster dives, and now they have parts. Repairing a seal usually leaves some sort of damage. It's usually damaged after you break in and get what you're going after. So oftentimes we'll just repair the damage we've done. For example, we might drill a hole, which we can then pick our way in. And then we just reseal the hole later. So there are a lot of different attacks here. There's a citation. You can get more information on these various attacks. Electronic seals. My personal favorite attack on electronic seals is the man in the middle. Now, somebody over here was talking about JTAG a second ago, and that sort of, to me, that means getting into the firmware and doing all that cool high. Well, you know, you don't really need to get that technical on any of this stuff, actually. Hijacking the display is a subset of a man-in-the-middle attack. So let's say you've got an electronic reader, which is reading some unique signature from the seal, and you've got an inspector looking at this reader. He's going to believe whatever the display tells him. So if you hijack the display, if you intercept the communication stream between the microcontroller and the display, you can now filter what's being shown on the display. If the microcontroller says alarm, alarm, and you filter that out and say okay, okay, the inspector has no choice but to believe that seal. So anyway, that's a very low-tech, you don't need to understand firmware, you don't need to reverse anything, you don't need to go, totally crazy. A lot of other different electronic attacks out there, but you can, cool the power crystals, you can cool the quartz crystals to slow the clock down. You can glitch attack the power line. All kinds of things you can do.
Well, one of the key points in any kind of security device, but particularly with seals, is that manufacturers and vendors claim often they have a unique manufacturing process that no one else can match. In our experience, that's usually not true, but it doesn't really matter, because what's often overlooked is an adversary doesn't really have to counterfeit a device. She's just got to make it look sort of like the original device and maybe have some kind of the performance features of the device. That's much easier than true counterfeiting. The average person is familiar with seals in the context of tamper-evident packaging required by law in the United States on all over-the-counter pharmaceuticals. Been remarkably little study on tamper-evident packaging. The FDA must approve it all, but doesn't really have any standards or guidelines or any explanation of how they approve or don't approve. So we did a little experiment. We went to the 7th Security Seals Symposium, and we had 71 tamper detection experts look at some products that had been tampered with. The work was done by a college student, Sonia Trujillo, which is a computer science major. And she basically attacked some and not others food and over-the-counter pharmaceutical products. And the results, as you might suspect at this point, was the tamper detection experts were no better than random guessing at which packages or containers had been tampered with. So the obvious question is, if experts can't tell, what possibilities does the average consumer have? And indeed, tamper-evident packaging is not about effective tamper detection. It's about reducing jury awards when inevitably there is product tampering. We're often asked about seal sport, a little bit like lock sport. Would this be a fun hobby? And in one sense, I wouldn't want to discourage that because I think it would highlight how bad seals really are, and in particular, how bad the average seal use protocol is. But frankly, right now, it's too easy. I don't see that it's that interesting a hobby. And the more important point is, what inspection protocol are you testing against? We can take even a very modest seal, and if you're willing to do enough work, do fairly reliable tamper detection. The problem is no one's willing to do that much work. So unlike a lock sport, where you just attack the hardware and it's either open or not, this is a much more complex problem. Well, the good news is most of the seal attacks that at least we've developed really have pretty simple and inexpensive countermeasures. But the deal is the seal installers and inspectors have to understand really what they're doing. They have to have seen examples of attacks on the specific seal for the specific application, for the specific vulnerabilities they have in mind. This is lots of hands-on training. Almost nobody, including for nuclear safeguards, wants to do this much work. On the other hand, we think that there better seals are possible. So the question is, what's wrong with current seals? Well, with a conventional seal, you can detect the seal being opened or the tampering or the intrusion, but what do you do with that information? In a conventional seal, you store it in or on the seal, the fact that there's been tampering or unauthorized access, maybe just from the seal being damaged. Well, we'd like to turn that around, and with an anti-evidence seal, when we first install the seal, we're going to store information in or on the seal. The tampering has not yet been detected. Then when it is, that gets immediately erased. Now there's nothing for the adversary to counterfeit. They can counterfeit the hardware, but if they don't know the correct anti-evidence information to put in or on the seal, they can't hide the fact that tampering has occurred. And indeed, we've developed, almost 24 different kinds of anti-evidence seals. They have a lot of interesting attributes. We think better security. They can sometimes go inside a container rather than having to be on the outside. They're typically 100% reusable. And they have something called an anti-gun decking feature. Gun decking is an old Navy term from the 18th century. When you were in the British Navy, if you wanted to shirk your duties, you'd go hide out on the gun deck, because unless a battle was underway, it was pretty quiet there. One of the problems with seals is the seal inspector, whether viewing the seal manually or with an automated reader, claims to have inspected the seal, but really didn't. Well, if you require them to report back the anti-evidence information, which they can do through non-secure communications channels, because the bad guy can only be a nuisance, he can't substitute in information to hide the fact that tampering has occurred. If you require this report in, the act of obtaining the anti-evidence is effectively the same as checking the seal. And there's an interesting possibility here, which makes most sense for international nuclear safeguards, namely treaty monitoring, where you can actually have the bad guys inspect the seal for you without the inspectors being present to demonstrate that there's been no tampering with the items that may have been dismantled or put in storage. We'll show you one anti-evidence seal here called the talking truck cargo seal. We developed this for a fictitious trucking company called Near Miss Trucking. Originally it was Acme Trucking, but it turns out there really isn't Acme Trucking, and we didn't want to get in trouble with them. Basically, the idea is that there's 125 slogans well known by employees of Near Miss Trucking. They're sick of these slogans. I've heard them so many times. They're not secret. But what is secret is the one slogan that's been chosen for this particular shipment. And here's just an example of some of the slogans. So the idea is when the truck reaches its destination, we're going to simply communicate with a radio frequency short-range device. It's going to provide a password, because this is a password anti-evidence seal, that says, I'm the good guy, it's perfectly okay to tell me the anti-evidence. And the anti-evidence in this case is a spoken slogan. So if the guys on the loading dock or the receiving dock hear the correct slogan, there's been no tampering. If they hear nothing or a different slogan, we like to feed the wrong slogan if there's been tampering so the bad guys aren't tipped off that they've been detected. Then they'll know that there's been some kind of tampering. So we'll go ahead and demonstrate this seal.
So here's the seal itself. If it looks kludged up, that's, well, because it is. We have a light sensor on it. Traditionally, we hate light sensors. They're very easy to beat, but they make for good demos because people understand them. Light sensors, well, yeah, they're just very easy to beat. So anyway, we're just going to turn this thing on. Now here's an example of an electronic reader.
ERMS Trucking Proprietary Security System, developed by Argonne National Laboratories Vulnerability Assessment Team, ready for programming.
Sorry about the intro, but we gotta.
I should say it's my voice because my students always said I'd like to hear myself talk.
Your hometown truckers. Your hometown truckers. Now monitoring.
Okay, so the slogan chosen for this period is your hometown truckers. This thing could be sitting in a warehouse, might be in shipment, who knows. When it gets inspected, you inquire, and if it hasn't been tampered with, you hope to hear the same slogan.
Tamper Inquiry 1. Your hometown truckers. Your hometown truckers. Your hometown truckers.
Now, if you've got some sort of adversary that gets in your container and doesn't know how to work in the dark, and they trip the light sensor, you come back in inspection time and you inquire, you hope to hear, or you should hear a different slogan.
Tamper Inquiry 2. Your cargo is safe. Your cargo is safe.
So why do we do a different slogan? Well, we don't want to tip our hand that you've been caught. If they can go to the microprocessor, which is pretty easy because it's sitting right here, especially on this model, they can see that, well, a byte's there or not there. In this case, we just swap out a different byte, and you're none the wiser. So the original byte's gone completely, new byte's been inserted.
The key point is once tampering or intrusion is detected, the information needed to generate the correct slogan is instantly erased within less than a microsecond, so that information is gone. Now, the adversary can counterfeit the hardware, but without knowing what the right slogan was, they basically have a problem.
So this is assuming that they don't know that you have this piece of hardware and how to reach the slogan.
Yeah, the question was whether the adversary knows about whether you have this piece of hardware and how to access the slogan. There essentially is a password, and the electronics are looking for an attempt to hack in or a physical intrusion into the actual microprocessor. So the hope is that the sensors that are associated with the device itself, including the seal, would detect any attempt to go in and try to get the slogan. But certainly if anyone can break in and get the slogan, then there's a problem. The slogan itself is not stored in the reader, but is actually stored in the seal. Yeah, one more question. You potentially could, but without the password, the seal refuses to respond. It's random. So, and you don't know the correct slogan, so you would.
Roger. Roger. Mm-hmm. Yes, you could, but the slogan that's chosen is supposed to be a secret. And if you're the bad guy, you don't hopefully know what that secret slogan was that was chosen for the...
In your own list of how to crack a seal, you said inside man. I got an inside man, I've got the secret.
Yeah,
that's true. If you've got the
secret, inside man would compromise. Absolutely, an insider threat compromises any security device.
If I say I have a reader, I can't tamper with it. I keep opening the door where I eventually just get back to the right one.
Well,
It's random, but
right.
if I roll the dice enough, I get it right.
Well, essentially, this is designed for a one-time opening. Now, you can program in, sometimes cargo stops several different places, but typically, the typical scenario is a company shipping from here to there, and it just should never be opened. So you're not typically going to be allowed multiple openings, but it's a good question.
Did your identifier also give a universal sequence as to when the inquiry occurred? At the first, it was, first inquiry, second inquiry. So if you've done it multiple times, then you would know it.
Well, the question is about the initial, when you hear the first slogan, that's, of course, done at secure shipping locations. The adversary is hopefully not present. Now, if he intercepts the slogan at your shipping department. Oh, absolutely. Right. Essentially, no technology takes away the problem of the insider threat. That's a serious problem with any kind of security device. Let's move on. We can take some more questions at the end. But these are great. These are the kinds of questions that need to be asked and are often not asked about tamper-indicating seals. Thank you. We initially thought that anti-evidence seals had to be electronic so you could have something to erase, but that turns out not to be the case. This is a very crude prototype called the magic Slate seal, where you essentially write some secret letters and numbers around the cylinder there with dry erase marker. Amazing technology, actually. So serious engineering went into that, so it doesn't dry out over time. And essentially what happens is the good guys know how to dial the front end of the device. They choose one of the 6 letters in a way that as this sled at the lower right-hand corner slides past the cylinder, it erases all the dry erase marker except for the one that lines up with the slot. And so that one number is saved. So essentially it's a password anti-evidence seal. The good guys know which letter to dial in, and that preserves the information. If the bad guys just randomly open the seal, they run the risk a 5 in 6 chance of erasing the secret anti-evidence information. And if we want better odds, we simply design it like a bike lock, where you have a series of rings with slots that have to line up before the lock can open. But the idea is the secret anti-evidence is inside the seal, and the act of opening the seal without dialing in the correct combination erases that anti-evidence. So the inspection involves opening it properly and then looking to see if the secret information is there and correct. And this is something called the time trap, which we also call the Xmucane seal, which is a great name for Xmucane. Xmucane is the Mayan goddess of time. Now, this is an anti-evidence seal. It doesn't need a password. In fact, it doesn't even have a reader. This typically goes inside a container. It doesn't care who opens the container, the good guys or the bad guys. It uses whatever sensors make sense for that application. But once the container is opened, it displays on the liquid crystal display a time, either absolute or elapsed time, and then it authenticates that time with a 2-letter hash. Basically, there's an algorithm that computes based on the time and a secret key that's known at shipping time exactly how to compute that 2-letter hash. Once it does this, though, it instantly erases the algorithm and the secret key needed to compute the hash for future times. So the problem the bad guys have is they don't know which time to put on for when the good guys are going to later open the container. But more importantly, they don't know how to compute the 2-letter hash that would authenticate that time. So to inspect this, you simply look at the time, see if it's reasonable, and then you check the hash, which you can do by reporting back to headquarters through non-secure communications channels, or you can have a little handheld reader we've built that'll compute the hash for you, given the assumption that you know the secret key, which is different for every shipment. I've done some work with wine. Wine turns out to be a huge problem for both tampering and counterfeiting. People buy really expensive wines, drink the good stuff, put in $2 chuck, and send it back out for auction. And the wine snobs are embarrassed to admit that they got taken, and it's a huge security problem. So we've developed this relatively inexpensive device that does both tamper detection and counterfeiting. If you want to do the authenticity check, you plug it into the internet, and it calls back a virtual numeric token, and you can check for authenticity. And then the seal that's present in the cap will detect if the bottle's been opened. It's not a lock. You can take this cap off anytime you want, but that's detected as a tampering event. It turns out one of the problems is we could make this thing really, really inexpensive, and that's not good. If you're going to do wine security, there has to be a snob appeal. And so the people we were talking to really wanted this to sell for $50. We think we can make it for a couple.
I was griping about light sensors earlier. What we like better than just light sensors are color sensors. Whoa. Are we?
I think you're good.
Yeah.
Fail.
Next slide, please.
Let's switch over.
There we go. Okay, I looked just last night at Mauser Electronics. You can find a color sensor for $2.44. Color is much nastier to defeat than, say, light level. What you do, it takes a little bit more work, but if you colorize the inside of a volume and you've got an acid in there, it can integrate the color inside the volume, and if that changes, hand comes in, shadow, whatever, then it trips. That's much nastier than just a light level, which you typically go for low light levels and you're doing good as a bad guy. Another thing that drives me crazy, it doesn't make sense at all. You know those little magnetic door sensors and window sensors? Those are all binary. They're either low or ground or 5 volts or 3 volts or whatever the system runs at. So either you shunt the system or you jumper it or open it up to circumvent. In fact, instead, they could use a Hall effect magnetometer, which these things are cheap, dirt cheap, and they provide an analog signal given a particular field value. So if you've got a magnet, this thing learns the field value when the door's closed. Then if a new magnet comes in to, say, spoof the system, that changes the field vector, you set off the alarm. Nobody's doing this. It doesn't make sense. Why? It's just, right now, the stuff out there is just way too easy to defeat. There are a lot of very cool sensors that could be used in security that aren't. Yeah? Gentleman has a very good point. If somebody sold a system that really actually worked, he could only sell it one time. So that's a very valid point.
This is another type of seal we like because it's really easy. Rare earth permanent magnets are very inexpensive now. The idea is if you've got a vault or you've got a cargo hold, you're going to sprinkle a bunch of rare earth magnets at random orientations and strengths throughout the cargo or the assets. If it's cargo, you're going to glue them down and glue down the pallets so the cargo doesn't move around. But now you're going to sit outside the vault or the container and measure the magnetic field, the complex three-dimensional magnetic vector field from all these rare earth magnets. That's very easy to do nowadays with some very nice commercial off-the-shelf magnetometers. They typically have a few nanotesla resolution in comparison to the Earth's field of 55,000 nanoteslas. They have a huge dynamic range of more than 6 orders of magnitude. What this means is if the bad guys go in and move something, they have to put it back with typically micron accuracy in 3 dimensions and arc-second angular precision. Now, if you don't want to push it that far because of the huge dynamic range, you don't have to measure with that kind of sensitivity. Now, can you put things back with that kind of resolution? Well, sure, but it's kind of time-consuming, so it's not a bad approach. But we can make life more difficult for the bad guys by simply scrambling the magnets when the door is opened. Now, this isn't how you'd really implement it, but it's a very simple approach. It's what we call the hamster wheel. It's on the inside of a door, and inside is a rare earth magnet that's been potted in some clay that's multifaceted. When you open the door, the magnet tumbles on the hamster wheel. When you close the door, it goes back to a completely different position and orientation. So you can sit from outside the door with your magnetometer, measure the magnetic field, and then leave, come back later and make another measurement, determine if the magnet's moved. Now, the way you would really do this is implement it in the door jamb. When the door is closed, the magnet's trapped in some position. But when the door is open, it gets tossed like some dice, tumbles around, lands in a new position, gets trapped again when the door closes. So very, very simple kind of approach. This is another kind of using very simple materials, again, very reusable. This is what's called bead in a box. We're going to show you a technique here called the blink comparator, something from the 1890s. It's the way you find planets and asteroids. You take a picture of the night sky, come back the next night, take another picture. You then blink or show each of the 2 images in a registered mode. Anything that's different will be interpreted by the brain as movement. So what we have here is a bunch of multifaceted balls. We've got a wooden box inside there that's got the valuable asset of interest. And we simply have some foam and we squeeze the lid down. And now you're going to see a blink comparator initially with nothing happening. So there isn't too much difference between the 2 images. But then I'm simply going to open the lid. I'm not even going to reach in and grab the asset. And so you can see just by looking at this comparison of the 2 images without having to think or run complex computer algorithms that there's a great deal of difference. Bad guys have to put all these balls back right, and they can't glue them because when we open the lid, we're going to check that they are free. This is a good way to check for adhesive label seals to see if they've been tampered with. And you can tell if somebody's been messing with things on your desk. It's a very powerful technique, very easy to use if you use a kinematic mount that repositions the container and or the camera very, very accurately. These things are very inexpensive, very easy to make or buy. So you don't even have to bother registering the image. So this kind of beads in a box approach is really nice because you can simply reuse the beads. You just need a before and after picture. And of course, you must secure those pictures. Well, we think there's still problems with our anti-evidence seals. We think it's a better way to go. But the real problem is nobody's really interested. There's not much demand for good seals. The Department of Homeland Security is interested only in what's commercially available now. Very little research goes on with tamper-indicating seals. The people who make seals are selling them just fine, thank you very much. They don't need to produce a product that competes with their product line. So until people have more interest in having better tamper detection, I think it's sort of a dead end. And there's some other issues that are typical for all kinds of seals having to do with battery life and secret key hash or password control and erasure issues, data remnants, and so on. And we're not convinced that our crude prototype designs are the best implementation for anti-evidence. But we think that really fundamentally this is a much better approach than conventional tamper detection. Now, let me go back a step and demonstrate for you the magnetometer, because if you haven't seen how sensitive magnetometers are nowadays, it's pretty impressive. So we'll just do a switch over to video here. What I have here is a rare earth magnet, maybe 30 cents. And I'm going to keep it well away from John here. And also my credit cards. So that looks like an absolute reading. This is a 3-axis magnetometer. Measures in nanoteslas. The Earth's field's around 55,000 nanoteslas, vector sum of the x, y, and z axes. And then he's going to zero it just so we can measure changes. So it's not quite zero, but the device needs some warm-up time. So it's around 0 for x, y, and z.
Stop moving around. That would help me.
Oh, sorry.
Thank you.
Okay, ready?
Almost. I want to get back to X. There we go. Yeah.
Okay, now I'm going to come closer here a little bit. I'm still, 10 feet away.
There's X, Y, Z.
And as I rotate, you can see that changed. And then just to demonstrate the seal aspects, I'll move much closer here, let them read 0. While I was doing that, I remind you that magnetic DC fields travel through almost everything without substantial attenuation, even most metals. Now, the metals will deviate the vector lines, but it doesn't really attenuate them. Unlike static electric fields, which you can shield with a Faraday cage, it's really nasty to try to shield magnetic DC fields. So he's zeroed it here, approximately. Well, this guy sells for about $2K, but you can buy the sensors for $10, or maybe $10 to $75. And you get, you're trading off sensitivity a little bit. Okay, now what I'm going to try to do is I'm going to remove the seal, and then I'm going to try to put it back as good as I can, just visually. So you move it, and you'll see a big change, of course. And I'll try to, obviously I could do better than I'm doing here, but you'll see I don't put it back all that well. So there's your seal. You can take the magnetometer away between measurements. And finally, just concluding, we think that the anti-evidence approach makes a lot of sense for real-time monitoring, where you're getting a real-time update about whether there's a problem. So instead of sounding an alarm, which a traditional cargo security system, for example, would do when there's tampering or intrusion, the problem with that is the alarm can be easily blocked. What we do instead is simply send an occasional all OK signal, which would be a simple bingo number, typically every minute or two. And we're just going to listen to that as the cargo goes down the road. So unlike traditional cargo security systems that are streaming high bandwidth information out of the truck, telling the whole world there's something really interesting inside the truck, we're basically sending a bingo number every minute or two. Very low bandwidth. We don't talk to the cargo, we just listen. So there's no hacking in from radio frequency approaches. And again, it's an anti-evidence approach, meaning that if intrusion or tampering is detected, we just quit sending the bingo number. So as long as the correct bingo number arrives, and only the good guys know what the correct bingo number is, the good guys and the cargo, then everything's fine. As soon as the all okay signal quits coming, then we immediately detect that. I think we'll skip this. I'm kind of running out of time here. So finally, if you'd like more information, we've got a book that's coming out shortly having to do with the idea of the weakest link in the chain of security. There's a lot of physical security books that offer insipid advice on how to do good security. Well, our book's going to offer insipid advice on how to have bad security. Because in the end, it's the mistakes you make that are more important for security than what you get right. That's because the bad guys don't attack randomly, they attack at the weakest link. And also, we are hosting the Journal of Physical Security. This is apparently the only peer-reviewed journal that's devoted to physical security, and it's free and online, and you can sign up to be notified when new issues come out. And if you'd like to download a whole bunch of reports, papers, and presentations on tamper detection and seals, including how to use existing seals better, you can find that at this website. Thank you very much.
Just a quick comment with that journal. We could really use paper submissions, especially from an audience like this. Typically, we get paper submissions from folks out in some company somewhere. Oh, we put in this burglar system and it seems to work. But folks from you or submissions from you folks would be just great if you don't mind throwing some papers our direction.
I guess maybe we have time for a couple of quick questions. Yeah. Sure, it's not too different from a traditional seal, which has a serial number. And if the bad guys... let me repeat the question, sorry. Question was about, again, the insider threat and what if someone intercepts the information. Because as he points out correctly, for at least some of these seals, you need to send information to the receiving location about what they're supposed to see. That's not the case for all the seals, but it is for some of them. Basically, you have essentially the same kind of problem, a little bit different with a conventional seal. You want to protect the serial number, at least for a little while. Typically, on a conventional seal, the serial number is on the outside, and the bad guys can get a look at it. Hopefully, with the anti-evidence seal, you've run the information through a completely different channel, one that you would use cryptography on. But once again, if you've got disloyal people, all bets are off. Technology doesn't save you from that. The other thing to point out is these seals aren't always just for cargo. Sometimes they're just for a vault. So you may stow stuff in a vault and want to come back later. So there's no, in that case, communication of information. You're just going to keep the reader, and you better secure it. But you're going to come back with that same reader and see if things change. In that case, you don't need to transmit any information. Any other questions? Yeah?
How do you deal with out-of-band auditing? In other words, people that are not privy to the knowledge around the seal but still need to validate it. Like, for instance, an inspector at a truck stop or TSA, which I do a lot of work with. They have to inspect in line as they're going through, but you don't want them, they're not sharing the secret information that you're sharing.
Right. The question is when you have multiple players involved. And the example I'd give is customs often have to open trucks and take a look. They don't do much. They just kind of stare at it. But in that case, with a seal like this, you want to program the option to have multiple openings, possibly with only allowed windows. The nice thing about microprocessors is that's all trivial to do. So if you've got a situation where you suspect a seal would be open in a certain time or location, or even if you don't, you can program in a certain number of allowed openings, and you simply go to new anti-evidence. Now, is that as secure as having only one piece of anti-evidence and assuming only one door opening? No. But is it as secure opening the door a bunch of times with a bunch of different people? No. So those are the kind of trade-offs. If you want good security, only one guy should open the door. But as you point out, that's not always possible. Yeah, back there.
I presume with the magnetometer that it's important to reproduce where it's placed or mounted in relation to the sensor. And then I have a question about whether magnetometers are calibrated individually or
There's a question about magnetometers, about calibration sensitivity, and whether you have to position them accurately. The answer is yes, you absolutely have to position them accurately. That turns out to be a problem solved in 1885. Kinematic mount, fabulous device. We can talk about it in more detail. It's basically 3 steel balls, like in ball bearings, that sits in a cone, a groove, and a flat. Not a precision device. You can just make one in your garage. Yet when it is set down, it will reproduce the position with extraordinary accuracy. And it's even to first order self-temperature compensating. Amazing device. So yes, you can re-register these images if you shoot them from slightly different positions, rotations, or angles. But if you use a good kinematic mount, the problem's essentially solved for you. The devices are so good, they're so good in absolute accuracy, that you really don't have to calibrate them nowadays. You're going to pay a little more for that kind of device. But in the end, we're mostly looking for changes, and typically fairly large changes, unless you really want to push the technique to incredible sensitivities.
But can you use a different magnetometer? Does it have to be the same one?
The question was whether you could use a different magnetometer. Answer is yes, there's some issues there. It's not totally trivial, but it's not nearly as difficult as you might think. Yeah, question.
One of our internet viewers has asked, is the U.S. doing competitively better or worse for using seals for nuclear weapons and WMDs than other countries, specifically the Soviet Union or other places?
The question is whether the United States is doing a better job with seals and tamper detection for nuclear safeguards compared to other countries. No, I think my personal view is it's a mess all across the world. We really don't have effective tamper detection. Especially for international nuclear safeguards. A little bit better situation in most countries for domestic nuclear safeguards. But again, my view is it ought to be a lot better than it is. Any other questions? Yeah. Well, that's, again, some interesting semantics. Some people insist it's nuclear security and safeguards. Other people insist it's only nuclear safeguards. There's 2 kinds, and people confuse them all the time, including people who work in the field. There's domestic nuclear safeguards, where we want to stop the bad guys from wandering off with a nuclear device. And there's international nuclear safeguards, where we're trying to determine if a country is abiding by its promises vis-a-vis international treaties. Now, that latter is an extremely difficult problem. Number one, the adversary is a nation, very sophisticated technologically. But number 2, everything's all backwards. In a traditional security application, the good guys own the assets and the facilities where they're stored. The bad guys try to break in and get to them. With international treaty monitoring, the bad guys own the nuclear assets. They own the facilities. The inspectors are not going to be allowed in much of the time. The people being inspected have to have entire circuit diagrams, all the software information for the devices. They may actually have to provide them. So you're in a situation where the burglars are providing the burglar alarms, maintaining them, and not allowing the inspectors access to the whole operation. So it's completely backwards, an extraordinarily difficult kind of security problem, but one that really, I think, hasn't had the kind of creative approaches really needed. The domestic nuclear safeguards one is a lot better shape, but even that, I think, needs a lot more work. Anything else? If not, well, thank you very much.